So, this is the second session on boiling heat transfer, and today particularly we will try to see nucleation from cavities and onset of nucleate boiling. But before going to this topic, I will try to do little bit recap from the previous session and maybe try to discuss one or two intricate points which probably may create confusion among us. So, if you recall, then I mentioned in the previous session that the boiling curves which we discussed, these are applicable for the sizes of the heaters which are significantly larger than the size of the bubble. Now, if you recall, one point I mentioned that if I have a vapor forming at a nucleation site. So, once this solid surface which is a heater surface, it is in contact with the vapor medium, then the rate of heat transfer will be less because of the low thermal conductivity of the vapor. And as this vapor will keep on growing, of course, the vapor contact will keep on increasing and more of the area near this nucleation site will be having lesser rate of heat transfer. And when this bubble will be leaving the surface, after that this area will be wetted by the fresh liquid which is coming from the top, and in this scenario we will be finding that the liquid thermal conductivity will be higher, which is in contact with the heater surface, and we will be having more rate of heat transfer. So, you can see that whenever I am discussing a particular site at which bubble is first evolving and then this bubble is actually departing and this area is wetted by the liquid, we are finding that at that particular location rate of heat transfer will not remain constant throughout. But some of the boiling curves which we discussed, there we mentioned that we have to maintain uniform wall heat flux condition. Okay. So, this is a contradiction, like we are saying one way that we are maintaining the uniform heat flux, but other way from the fundamental idea of bubble evolution, we are understanding that rate of heat transfer will not be remaining fixed. So, there will be changes in the rate of heat transfer. So, the point is, whenever we are talking about the rate of heat transfer or maintaining the condition of uniform heat flux, we have large amount of heater surface area whenever we will be considering in a two-dimensional view, and it may so happen that these circles represents the nucleation sites from where bubbles are growing. Okay. So, as a whole, it may so happen that at a particular time instant, I will be having almost same number of nucleation sites which will be in the active process. Ultimately, what will be happening? From some of the nucleation site, there can be departure of bubble and re-wetting because of the fresh liquid, whereas some of the nucleation sites may have formation of the bubble. So, as a whole, when we are able to maintain this condition that the length scale of heater surface is significantly large in comparison to the length scale of the bubble, over this scenario we will be finding that on a heater surface more or less I will be having almost uniform liquid and vapor contact. So, if I have almost same fraction of the liquid and vapor contact throughout the entire process of nucleation, in that scenario I can say that the portion of the surface where there is liquid contact, there may be slightly low rate of heat transfer, but the portion where there is liquid contact, there will be higher heat transfer, and all together when I will be defining the average value of the heat transfer for the entire surface, that will be maintained in terms of uniform heat flux. So, ultimately whenever we are plotting the boiling curve, what we do plot is actually average value of heat flux. So basically we plot average heat flux from the heater surface. Okay. So though there can be localized fluctuations at different locations on the heater surface, but as a whole, as we are plotting the average value of the heat flux, it will be remaining same. Similar situation is true even temperature constant, there can be again smaller fluctuations of temperature at different locations of the heater surface. Ultimately, we may not be able to control the temperature so precisely that each and every point on the surface is actually finally very precisely maintained at the constant surface temperature condition. So, as a whole, because in the previous lecture the idea was about the macroscopic. So, whenever we are referring to the macroscopic quantities, we are referring to the average quantities defined for the complete surface area. Okay. Is this point clear? So, maybe this is something which we can take from the previous lecture. Now, one important statement I will make which will be forming the basis of this entire lecture. So, first point is no material can nucleate if any gaseous phase is present in its surrounding. Okay. So, if I say there is bulk of the liquid, it is extremely challenging for liquid to get converted into vapor from bulk. So, it requires certain amount of gaseous phase from where the identical vapor like molecules will be forming and nucleation will be starting. Unless or until I do not have any gas contact, for example, you can understand this process very simply. So, when we say evaporation, in case of evaporation what happens? If I say maintained, if I have kept a water in a glass in this room, and if I see tomorrow what is the level of water in the glass, that will be slightly low if my air is not saturated in the room. So, ultimately you will be finding that vapor is actually, or molecules of the water from liquid phase is entering into the gaseous phase. So, typically this transfer of liquid molecule into the vapor is only taking place at the top surface of the liquid where there is gas in the surroundings. In the similar way, whenever we do heat water in a pan, so typically though we say that whatever the boiling curve we have plotted, that is for actually smooth surface, but in reality no surface will be precisely smooth. Even we are doing the machining, because of the machining process we may find that large number of surface irregularities can be over the surface. So, ultimately we see the mean profile of the surface only. So, whatever appears to us from the macroscopic point of view, that is nothing but mean profile of the surface, whereas below this nominal profile of the surface I will be having lot of protrusions or cavities, and in these cavities there will be some amount of gas entrapment. And typically you will be finding that the conversion of liquid molecule in the vapor molecule typically takes place at this liquid gas interface. We never find in case of boiling process that we have some bubble which is nucleating from the bulk of the liquid. So, it means that this is kind of a practical observation also to us, that whenever vapor starts forming, it typically forms from the interface in between the gas and liquid. So, liquid has to be in contact with the gas or it with its vapor, then only there will be actually conversion of liquid into the vapor phase. Now, and once this conversion is taking place, after that also whatever amount of vapor bubble is formed, it is not always true that all the vapor rising from the cavity, will be actually able to sustain in the vapor phase only. So, it may so happen that the vapor forming from the cavity, either it may not at all grow, or if it is growing and after departure, if it is entering into the bulk of the liquid, if from vapor to liquid rate of heat transfer is more, then this vapor will be ultimately dying down. So, it means that for vapor to form, there has to be some amount of temperature condition which should be satisfied in order for that vapor to sustain and further grow. If that condition is not maintained, then that vapor cannot continue. So, let us understand this condition with the help of a very simple example. If I take a pool, this is the pool of water, and let us consider that the temperature of water is TL. Now, in this, I have a vapor bubble which is of spherical size, spherical shape, and let us consider the radius of this bubble is RB. Okay. Now, I will be having some PL as the liquid pressure and PV as the vapor pressure. For this bubble to be in equilibrium with the surrounding liquid, its temperature should be same. So, if TL is the temperature of the surrounding liquid, then the temperature of the vapor bubble should also be TL. So, I will be writing TV equal to TL, where TV refers to temperature of vapor bubble. Is this point clear? Now, if you see, we know that PV minus PL, because of the Laplace equation, has to be equal to 2 sigma by RB. Is this point clear? It means that pressure inside the bubble, vapor volume, has to be greater in comparison to pressure in the liquid phase. Another important point is, if I consider that this vapor is just nucleated, if it is just nucleated, then this vapor has to be in the state of saturated vapor state. What it means that if I slightly remove the heat from this vapor will actually start condensing. So, this vapor has to be saturated because it is a just nucleated vapor. So, if it has to be saturated, it means that temperature of the vapor, which for having thermal equilibrium with liquid is equal to TL, has to be equal to T saturation at the given value of the vapor pressure. Is this point clear? Because this is just nucleated, so it has to be equal to saturation temperature at the pressure, given pressure of the vapor. Now, if you see, we have this PV diagram. So, typically on PV diagram, liquid vapor domes appears something like this. Now, on this PV diagram, I will be having one line corresponding to pressure PV, and I will be having another line corresponding to pressure PL. And I know that from the previous discussion that the temperature of the vapor is equal to saturation temperature at given pressure. It means that the state of the vapor bubble, if I have to represent on this TS diagram, it will be my this point. Is this point clear? So, this is nothing but state of vapor bubble. All are clear with this point? Now, if you see, what is this difference of pressure? This difference of pressure, of course, will be equal to nothing but 2 sigma by RB. So, 2 sigma by RB is the difference of the pressure. Now, if you go to the previous slide, you can see that your PL is less than PV. Is this point clear? PL is less than PV, and the temperature TL is equal to T saturation at PV. All are clear with this point? Now, if I say that corresponding to pressure PL, I have temperature T sat L, then I can say that the temperature of the liquid is actually greater than T sat L. Is this point clear? All are clear with this point? So, it means that liquid outside the bubble is at pressure PL, but it is not at saturation temperature for this pressure. The temperature of the liquid is greater than the saturation temperature available at PL. All are clear with this point? So, what can happen? I can say that now the state can be represented in such a way so that it is in liquid state only, but its temperature is greater in comparison to T sat at PL. So, T sat at PL will be a temperature line passing through this saturated liquid line, whereas I am having some T saturation corresponding to this. So, that is nothing but my TL, which is equal to T sat at pressure PV. Okay. So, ultimately this TL line has to extend to pressure PL in order to define the state of the liquid. Is this point clear? Ultimately, TL is the temperature of the liquid and its pressure is PL. So, it means that the state will be defined at the intersection of TL and the PL. So, for this line to intersect with this line PL, my temperature line will be extending something like this, and ultimately this temperature can maximum go up to some pressure limit. After this pressure limit, it will not be able to go below and it will be again jumping to this point. So, are you understanding this point? This TL temperature has to cross the pressure PL in such a way so that it is intersecting over here in order to define the state of the liquid which is just outside the bubble. So, now you can see that this particular line is at higher pressure or at higher temperature in comparison to saturation temperature line corresponding to pressure PL. So, that is why I can say that the liquid which is just outside the bubble, it is in nothing but superheated state. So, till now we have only, whenever we study the basic thermodynamics, we typically only say superheated state to vapor, okay. But superheated state of vapor can only take place when boiling is taking place from a flat interface, because in case of flat interface what will be happening, the radius of curvature will be infinite, which will be making 2 sigma by infinity equal to 0, and ultimately the pressure on vapor side will be equal to pressure on the liquid side. So, whenever I am able to maintain very large bubble which is almost identical to a flat interface, their liquid can evaporate even at the saturation temperature condition. But whenever I am considering a curved interface, because the pressure of the vapor has to be greater in comparison to pressure of the liquid, and in order for that particular vapor bubble to sustain, there should be thermal equilibrium in between the vapor bubble and the surrounding liquid. That is why the liquid has to be at a temperature greater than the saturation temperature for the given liquid pressure. So, this type of state, because typically when the temperature of some substance is greater in comparison to the saturation temperature at the given pressure, we call that substance as nothing but our superheated state. So that is the reason I will be calling this liquid as nothing but my superheated liquid. Is this point clear? So it means one point is very clear to us, that a vapor bubble will only be able to sustain in a system if the liquid outside this vapor bubble is in superheated state. And this is the reason because of which the constant temperature line, which thermodynamically for a flat interface moves like this, for a curved interface it has to move in this particular fashion, and it forms a spinodal curve. It forms a spinodal liquid and spinodal vapor curve. And another important point is, this goes only up to a minimum condition where del P by del V at a given temperature negative value is satisfied, which is the condition required for mechanical equilibrium. Whenever this del P by del V condition is not applicable, then the state will be immediately jumping from this point to this point. It will be jumping from liquid spinoidal to the vapor spinoidal. Is this point clear? So one point we have understood now, that for a vapor bubble to stay within a liquid pool, the liquid which will be in the surrounding of the vapor, that has to remain in the superheated state. If that liquid is not in the superheated state, then that bubble will not be able to sustain. Okay. Now let's, with this understanding, let's come back to our original idea, which is nucleation from cavities and onset of nucleation boiling. So before that, let us first start. So typically the nucleation can be defined into two ways. One is homogeneous nucleation and other is heterogeneous nucleation. So whenever the nucleation of a liquid to vapor is taking place in the bulk of the liquid, that particular type of nucleation is referred to as homogeneous nucleation, and in most cases in terms of cavitation phenomenon, this type of situation is actually observed. However, when the nucleation of a bubble is taking place from some solid surface, that particular type of nucleation is referred to as heterogeneous nucleation. Now we have already studied that in practical scenarios, no surface will be perfectly smooth and we will be having some surface irregularities on that surface. However, whenever we are doing the theory, there is no restriction of making any assumption. So in theory, we can start with the assumption that our surface is actually perfectly smooth and there is no irregularity on the surface. So if I assume that I have initial state where my liquid is filled inside a container whose temperature is TL and pressure is PL, and the bottom face of the container is perfectly smooth. The meaning of perfectly smooth surface is that it do not have any type of surface imperfection. There is no perturbation, there is no cavity. Now, if I assume that a vapor, initial vapor volume is there, whose temperature is TL, pressure is PV and radius is R, and it is making an angle theta, contact angle theta on the surface. And of course, surrounding temperature will be TL, pressure will be PL. So this type of nucleation, which is taking place on a perfectly smooth surface and purely taking place because of the initialized vapor condition, this type of nucleation we will be calling as heterogeneous nucleation at a perfectly smooth surface. In order to analyze this, what has been done from molecular kinetic theory perspective, analysis is done and one parameter J is calculated. This parameter J represents the rate of growth of the bubble which we have initialized. if I plot this rate of growth of bubble as the function of liquid temperature, which is my temperature outside. So, I will be finding that for water at 101 kilopascal, this equation, when I am plotting it for perfectly wetting surface, which is having contact angle theta equal to 0, this curve is something like this. And here you can see this growth starts from temperature close to 298 degrees Celsius, and then it is say increasing, and of course it is plotted somewhere close to temperature 310 degrees Celsius. You can see one important point over here, that I am considering water, and water is at 101 kilopascals. So, 101 kilopascal is nothing but its atmospheric pressure. Corresponding to this, what we know is the boiling point of water is 100 degrees Celsius, but the vapor volume which started growing, that started somewhere temperature close to 298 degree Celsius. Similarly, if you say increase the contact angle, you are going towards slightly less wettability, you will be finding that the required temperature is even slightly high, but it is in the same range. On the other hand, when the same equation is plotted for angle theta equal to 108 degree. So, you can see that for theta up to 90 degree, this entire theta quantity will be positive, this term will be a positive quantity, but whenever theta will be going above 90, this quantity will become negative. So, once it is becoming negative, it means the growth rate will try to shift towards the low temperature conditions, and particularly this, because this depends upon the relative magnitude of the entire terms. So, this transition starts somewhere in the range of 65 to 70 degrees Celsius. So, I will be finding that if I keep on increasing the angles up to 65 degrees Celsius, then this growth rate curve will keep on shifting towards the right, but when I go temperature close to 70 degrees Celsius, this curve will move on the left of theta equal to 0, and again it will move in the backward direction. But still you can consider that the required temperature is 280 degrees Celsius to 310 degrees Celsius, whereas the water temperature is actually boiling, saturation temperature is nothing but equal to 100 degrees Celsius. So, what it means? It means that if you have to boil water on a perfectly smooth surface, your heater temperature should be 300, close to 300 degrees Celsius, in order for the vapor bubble to grow at the heater surface. Is this point clear? However, whenever we start the boiling process, in our daily applications, what we observe? We observe that bubbles start appearing somewhere close to 10 to 15 degrees above the saturation temperature. So, if I maintain the heater surface at 110 or 115 degrees Celsius, then I will be finding that nucleation of the bubble will be starting, and ultimately the bubble will grow in size and then it will depart the surface. So, the reason is because the engineering surfaces, or whatever the surfaces we are obtaining from different manufacturing processes, these are not perfectly smooth. So, if the surfaces are not perfectly smooth, so whatever the earlier I have shown that these will be having so many perturbations, whenever you will be filling the liquid in the container, you will be finding that in all these irregularities, some amount of gas will actually stay. So, if some amount of gas is staying while you are filling the cavity, then you will be finding that there is an interface of gas and liquid, and interface of gas and liquid always promotes the conversion from liquid phase to the vapor phase. So, these are the sites from where nucleation of vapor will be actually starting. So, that is the reason, because gas remains entrapped within the cavities, that is the reason that we typically practically get the nucleation of bubbles at temperatures significantly less in comparison to the temperatures required on a perfectly smooth surface. So it means that if I have to understand the process of bubble nucleation, I must know how gas is being entrapped in the cavities. Because if I say that I have 1000 cavities on the surface, of course all the cavities will not be of same shape, size. There will be plenty of differences in the shapes, because this entire is actually random phenomenon. It may so happen that some of the cavities may have entrapment of the gas, whereas some of the cavities may not have. Okay. So, the cavities which will be having gas entrapment, probably these will be the active nucleation sites, whereas the cavities which are having lesser amount of gas, there we may not be able to see the nucleation. So, what are the required conditions for gas entrapment, and how that gas entrapment can lead to active nucleation sites, that let us try to understand. So, to understand this, what we will be doing, first we will try to see how vapor and liquid entrap in a groove. So, what we have done, we assumed that we have a conical groove. Of course, this is an assumption, because in reality there will be large number of irregular arrangements. So, from our analysis point of view, we are assuming that we have nothing but a conical groove. So, if I have a conical groove, then this particular wall is actually forming the wall of the conical groove, and the angle of the conical groove we are considering as equal to 2 gamma. So, here this angle is nothing but 2 gamma. Now, let us consider that when filling of the liquid is done on this conical groove in such a way that the advancing contact angle is greater than 2 gamma. So, if what is advancing contact angle? We have been studying about the contact line dynamics. So, if I have a drop, so here I will be having liquid, here I will be having vapor. Whenever the angle I measure from liquid side, whatever this angle is, and if this contact line is actually moving in outward direction, during that process whatever the angle I will be having, that will be actually advancing contact angle. And if contact line is moving in inward direction, then whatever contact angle I am having, that will be actually receding contact angle. And we typically know that the value of advancing contact angle, because of contact angle hysteresis, is always greater in comparison to the equilibrium contact angle, whereas the receding is less in comparison to equilibrium contact angle. Now, the situation is, this particular curve represents a liquid vapor or liquid gas interface, which is advancing. This interface is actually advancing into the cavity, it is entering into the cavity. So, when it is entering into the cavity, because this from liquid side contact line is moving, the angle over here is theta A1, and I assumed that the condition of theta A1 is greater than 2 gamma. So, if theta A1 is greater than the angle of the cavity, the curvature of the interface will be adjusting in such a way so that at some point of time while it is advancing, it will be partly closing the cavity. So, once it is partly closing the cavity, whatever the volume we have below this, that will be nothing but the amount of gas which has entered. Is this point clear? On the other hand, if you consider that your advancing contact angle is less than 2 gamma, then the situation will be more of hydrophilic, and this interface will be more flatter, and because of the flatter situation of the interface, this contact line will keep on moving and entire cavity will be filled with the liquid and entire gas portion will be displaced from the cavity. So, it means that for advancing contact lines, the condition is that if advancing contact angle is greater than 2 gamma, then during the filling of the liquid, in a container, my cavity will be able to entrap the gas. But if for certain cavity, the advancing contact angle is less than 2 gamma, there we will not be having any type of gas entrapment. Is this point clear? Similarly, if you see the receding contact line, so for receding contact line, we have two conditions. So first is when theta R1 is less than 180 minus 2 gamma. So this is the theta R1. So if this is the receding contact line, ultimately what is happening? This vapor or this liquid is actually trying to trap. So once it is trying to trap, it will be touching the surface, and once it is touching the surface, it means part of the cavity will be having actually gas. So over here also, finally we will be getting the situation that theta has to be greater than 2 gamma in a situation where gas can actually entrap within the cavity. So typically, whatever the cavities we are having, these can be of 4 types. One is cavities that trap gas only. Second is cavities that trap liquid only. There can be some cavities that trap both liquid and vapor, and some cavities which may not be able to trap both liquid or vapor. But mostly the condition which we need to satisfy is that theta advancing has to be greater than 2 gamma, whereas theta receding has to be less than 180 minus 2 gamma. So it means that if for a particular type of fluid with certain surface, I have more contact angle hysteresis, it means I will be having more and more value of advancing contact angle and less value of the receding contact angle. So it means higher contact angle hysteresis always promotes the gas entrapment. Is this point clear? Okay, now once this gas has entrapped, what will be happening after this point? So it is not the situation that whatever the gas has entrapped, that will always be remaining in the surface. So there are multiple phenomena which can take place at microscopic level, and these can affect the amount of gas entrained. So you can assume that this is your cavity and say this is the amount of gas which is entrapped, and above this is the liquid. So it may so happen that if liquid and gas combinations are chosen in such a way so that there is strong diffusion of gas into the liquid. If there is strong diffusion of gas into the liquid, what will happen in this scenario? Whatever the entrapped gas is there, slowly because of the diffusion process, it will start again mixing into the liquid phase. Second important point which will be controlling this process is solubility of gas in the liquid. So what do you mean by solubility? So normally we know that even our water at normal temperature pressure conditions contains some amount of gases entrapped in it. Okay. So it means it is having certain amount of solubility for that particular gas. So if the solubility of a liquid is strong for particular gas, then what will be happening? Whatever the gas has diffused, that gas will be entirely soluble in the bulk of the liquid, and that gas will not be able to stay at this particular cavity. So both of these situations represents the nothing but the post filling dynamics. Okay, these are representing the post filling dynamics. We have gas filled, but that filled gas can diffuse into the liquid, and if the solubility in the liquid is not there for the gas, then of course the diffused gas has to again come back to the cavity. But if solubility is there in the liquid, then it will be easily able to stay within that particular liquid. And in the scenarios where my diffusion rate is high and solubility of gas is also significantly soluble in the liquid, then this cavity slowly will be actually gas will be leaving out of this, and it will be entirely filled with again with the liquid even after the entrapment process. So, in this scenario, typically for boiling phenomenon to happen, whenever boiling will be starting, this is my gas, this is liquid. When boiling will be starting, some liquid molecules from this point will get converted into the vapor. So, now I am not having only two phases, I will be having simultaneous occurrence of the three phases. So, you can see this is liquid, this is gas, and in between I will also be having the vapor of the liquid. So, you can understand this process in this way. Whenever you are pouring water into the container, below at that time I do not have any amount of vapor. So, if I do not have any amount of vapor, the gases which will be entrapped in the cavity, that will be mostly all the constituents of air. But whenever nucleation will be starting, because of the nucleation process, because all the gases, these are already in the gaseous stage, our main purpose is to convert liquid molecules into the vapor molecules. So, when nucleation will be started, then I will be getting over here nothing but only H2O vapor molecules, H2O molecules, and all these molecules will be mainly in the vapor state. So, while these water molecules are forming the vapor state, it may so happen that these water molecules can displace this gas, and during the whenever we will be operating this particular cavity for large time period, it may so happen that after the cycle of 10 hours or say 100 hours or even say 200 hours, this gas is entirely gone from the cavity. So, if this gas is entirely gone from the cavity, then I will be finding that when pinch off of the bubble is taking place, then some sort of vapor residue is remaining in the cavity, some sort of vapor residue is remaining in the cavity, and this vapor residue will create nucleation for the next bubble to grow. So, this is perfectly fine when we are continuously operating the system, but this particular type of situation is having one disadvantage. What is the disadvantage? Say if I have stopped the system and if I have decreased the temperature below the saturation temperatures, in that case what will be happening? All this vapor which is present in the cavity, it will condense and it will form liquid. So, once it is forming the pure liquid, again what situation we have got? We have reached to the same situation of the nucleation of liquid from a flat smooth surface, because though the surface is having cavity, but this cavity is do not having any interface from where nucleation can initiate. Okay. So, in this case, when you will be again starting hitting the surface, you will be requiring again significantly high amount of superheat for the nucleation process to initiate, because there is no gas entrapment and you do not have the interface from where easily the nucleation can start. Is this point clear? So, maybe what we have to understand is that first characteristic of the cavity should be that it should be able to entrap good amount of gas while we are filling the liquid in the surface. Other than that, the other characteristic of the cavity should be that it should able to retain non-condensable gases. So, cavity should also be able to retain non-condensable gases. So, shape of the cavity should be in such a way so that even if we are repeating the boiling cycle, like we are heating the surface and then cooling the surface for say multiple cycles, but the amount of gas should remain intact. If non-condensable gas is leaving the cavity, then again the degree of superheat which will be required for nucleation to occur, that will be again significantly high. Is this point clear? So, a particular shape of cavity which is able to retain some amount of non-condensable gases, that is called as a reentrant cavity. So, reentrant cavity, you can see the shape of the cavity is something like this. This is the one phase which I can say is a non-condensable gas. Then I have second phase which I can say is a some liquid entrapped, and third phase which is a vapor. Okay. So, in this scenario what will be happening, even if I condense, then the vapor will be condensed, but this non-condensable gas will keep staying within the cavity only. So, it means that if I have to go for some situations where say whatever my heat transfer system is there, I have taken it shut down, I have stopped it, and even I have to start it again, then also it will be able to start the nucleation process easily. If the non-condensable gases are gone and I have not taken out the water, water is there within the system only, then this cavity will not function. Even what people have done, because I told you earlier that two important parameters are there, one is diffusion and second is solubility within the liquid. So, solubility should be less, again diffusion should be less, then only gas will be staying in the cavity. So, there are some experimental evidences where people have actually pressurized the system. So, upon increasing the pressure, actually we can increase the solubility of a gas inside a liquid. So, when people have repeated the experiment with normal pressure conditions and higher pressure conditions, typically at higher pressure conditions the gas solubility was more, and at higher pressure conditions it was observed that the number of nucleation sites were significantly less in comparison to the number of nucleation sites which were observed at the normal pressure conditions, where solubility of gas in the liquid is actually less. Okay, now let us consider a situation. We know now about that gas entrapment is required, from where vapor volume will be actually forming. But when this vapor volume will be forming, it has to grow. So, while the vapor volume will be growing, what should be the required condition? Of course, for a perfectly spherical bubble, I have already told you that the surrounding liquid has to be in the superheated state. So, here also it has to be in the superheated state, but what amount of superheat it has to minimum amount of superheat, what is the minimum amount which it has to sustain, that let us try to find out. So, again here what we are using, I am making the assumption that my cavity is conical in shape and the angle of the cavity is 2 gamma. Now, I can have three different situations. First, we already know that all the angles which I need to operate has to be greater than 2 gamma. Okay. But if I say that I have the angle in such a way that theta is less than gamma, but less than 90 degrees. So, in this situation you can see that I am towards the hydrophilic situation and angle has also to be less than gamma, then it means I am towards the more hydrophilic situation. So, if I am in more hydrophilic situation, my contact line will be adjusting in such a way so that the angle from the liquid side is actually very less. So, in this scenario you will be finding that if this is my vapor, this is liquid at some time t1 and this is vapor and this is liquid at some other time t2 and this is at some other time t3, I can see that initially the radius of curvature of this particular bubble is actually initially the radius of curvature of this particular bubble is very small, and as I keep on coming towards the tip of the cavity, this radius of curvature of the bubble is actually increasing. So, if I plot the ratio of capital R, which is radius of the cavity, divided by the radius of curvature of the bubble which is growing, I will be finding that initially this radius of curvature is very small. So, it means this R by R will be starting from a higher value, and as I am moving towards the surface, this radius of curvature of the circle is actually keep on increasing, and even once it crosses the tip of the conical cavity, then also over the flat surface, because of the less angle, this again forming a big circle. So it means R by R ratio is monotonically decreasing for the situation of theta less than gamma less than 90 degree. Okay. However, this type of situation is practically difficult to sustain, because in this case the chances of gas entrapment will be very, very less. Now, that we have already studied from the condition of the gas entrapment. Now, the second type of situation could be when my contact angle is in between 90 degrees and 2 gamma. So, again I am in the hydrophilic range, but angle is towards the higher side, close to the 90 degrees. So, in this scenario, if you see, initially the radius of curvature of bubble will be very large, and when the bubble is growing, then radius of curvature will keep on decreasing somewhere close to the point when bubble is reaching the tip. So, it means initially it is starting from a smaller value, but whenever it is again reaching close to the tip, the size radius of curvature of bubble will keep on increasing. So, I will be having some decrease in radius of curvature, and near the tip the radius of curvature of bubble and radius of cavity will be almost same. So, ratio of R by R will be close to 1, and after that again it will decrease monotonically. On contrary, if you go to a situation where theta is greater than 90 plus gamma, it means we are going towards hydrophobic situation. So, if I go to a hydrophobic situation, in this case what will be happening, my angle has to be greater than 90. So, if angle has to be greater than 90, then the interface will be adjusting in such a way so that the curvature of interface is now in the opposite direction. So, in the previous situation your circle was forming towards the downward side, now circle is forming in upward side. So, if it is forming in upward side, it means our value of R by R will be negative, because typically curvature normal to the interface, one direction we take positive and other direction we take negative. So, this is in the other direction, so it means R by R ratio will be actually negative. And when it is about to cross the tip of the conical cavity, then again curvature on the top portion will be actually adjusted in a positive way, and after reaching the peak I will be having again fall in the radius of curvature. Is this point clear? It means that one important point, that for a bubble to come out of cavity at angles greater than 2 gamma, value of R by R will be close to 1 or less than 1. Is this point clear? Because this peak point is corresponding to the situation when bubble is just crossing the tip of the conical cavity and coming out of the cavity. But once it entered into the pool, then again R by R value is decreasing, it means bubble has started growing. But it has to, when it is just coming out of the cavity, R by R is nearly equal to 1. And for the bubble to grow outside the cavity, particularly for situations where theta is greater than 2 gamma, R by R has to be less than equal to 1. Whereas the situations for which theta is less than gamma, in this scenario R by R is typically greater than 1 for the bubble to come out of the cavity. Is this point clear? So, it means these two situations now we have to dealt differently. So, the required degree of superheat or required minimum radius of the bubble which can grow, that will be different for r by r less than equal to 1, and it will be different for r by r greater than 1. Okay. Now, one important point is, so we have one equation which is PV minus PL equal to 2 sigma by RB. This is Laplace equation, and we also know that Clausius thermodynamically during the phase change regime, Clausius-Clapeyron equation should be satisfied, which starts from the Clapeyron equation, that is dP by dt has to be equal to HLV divided by T into VLV. Okay. So, in the phase change scenario, rate of change of pressure with temperature should satisfy this equation, which is known as Clapeyron equation, and when we integrate this equation for liquid and vapor phase, whatever the integrated equation we get, that is called as Clausius-Clapeyron equation. So, if we combine Clausius-Clapeyron equation and the Laplace equation, we get a situation where TL, so my bulk of the liquid is always at temperature TL and the pressure of liquid is actually PL. So, TL minus T sat at PL. One important point you have to understand now, which is from the previous discussion. Earlier I told you that the saturation pressure corresponding to PL is less in comparison to the pressure of the liquid. Liquid has to be in the superheated state. So, how much is the degree of superheat of liquid is required, that has to be greater than 2 sigma T sat at PL into VLV divided by HLV, and where R minimum we are defining the minimum radius of vapor bubble. So, this equation is typically coming from the condition of Clausius-Clapeyron equation. Is this point clear? So, if I combine Clausius-Clapeyron equation with Laplace equation, then what does this left side is representing? This I have already explained you. Again I am explaining. Say if this is my vapor, if vapor is at TL, this has to be at TL. But the pressure of the liquid, because vapor is saturated, so pressure of vapor will be PV and TL has to be equal to T saturated at PV, and T saturated at PL will always be less than TL. This condition we already know. So, what is TL minus T saturation at PL? This is something which is called as required degree of superheat of liquid. Okay. So, this is nothing but required degree of superheat of liquid. If I put in PV minus PL the greater than condition in order to satisfy the mechanical equilibrium, then this greater than condition will be coming like this over here, and it will be giving me the minimum required degree of superheat has to be greater than 2 sigma T sat at given PL into VLV divided by HLV and R minimum, where R minimum is the minimum radius of the bubble which can form at a particular nucleation site. Is this point clear? Now, one important point is how to decide this R minimum. We have to decide what should be the R minimum. So, typically R minimum will be nothing but the amount of gas which is staying in the cavity, because above that only vapor volume will be growing. So, the minimum possible radius of the vapor has to be equal to the radius of the gas which is entrapped in the cavity. So, what we can do, how we can actually calculate the R minimum? For calculating R minimum, what I can do, I can assume that if my contact line is advancing during the filling process and it is having angle theta, then at some point of time this contact line will be actually touching the top portion of the cavity. Once it has touched the top portion of the cavity, after that liquid will be actually displacing this vapor, and here I will be having some entrapped volume. If I geometrically calculate this entrapped volume, this is the V1 amount, and after filling, whenever cavity will be at rest because of the buoyancy and surface tension forces, this interface has to adjust in a curved manner. So, once this is adjusting in the curved manner, then the volume has to be equal, because this is the entrapped volume and this entrapped volume is actually readjusting itself in a curved manner. So, from this volume conservation, whatever the radius I will be getting, that will be my minimum radius which will be entrapped in a cavity, from where nucleation of the vapor will be actually starting. Is this point clear? Now, typically for the situations where R by R is less than equal to 1, there this minimum radius is found to be nothing but equal to the radius of the cavity itself. Is this point clear? So, the situations where R by R is less than equal to 1, it means the situations where theta is significantly larger than the angle 2 gamma. For these situations where entrapment is easily possible, there the radius of the bubble will be close to the radius of the cavity mouth. So, this is the mouth of the cavity and its radius is capital R. So, what I can do in my minimum required superheat condition, I can replace this R minimum with capital R, and this will be applicable only for R by R less than equal to 1. Wherever for R by R greater than 1, because entrapment is a challenging task, there we have to actually follow this volume conservation equation, and this volume conservation equation typically is experimentally is obtained, and it is found if I define gamma as ratio of R minimum by R, where R is the radius of the cavity mouth and R minimum is the initial radius of the bubble. That ratio omega is given in terms of function of contact angle theta and cavity angle gamma. So, here you can see for 2 gamma equal to 5 degrees, 9 degrees to up to 41 degrees it is given, and one interesting point you can see that if 2 gamma is 5 degree, from where this omega is starting? Omega is starting for theta value close to or slightly larger than 5 degrees, because if theta is less than 2 gamma, then entrapment of gas cannot be done. For entrapment of gas to happen, theta has to be always greater than 2 gamma. This is something which we have already concluded. So, even if for the very hydrophilic situations, we need to determine gas entrapment and minimum radius, that curve typically shows that this value of omega will be 0 when my theta is less than 2 gamma. You can see for all the cases, when you consider say 21 degree angle, so your curve omega is becoming positive somewhere from 21 degrees, and before that value of omega is typically equal to 0. Is this point clear? So, it means the previously declared condition theta greater than 2 gamma has to satisfy, then only entrapment will be taking place. Is this point clear? But important point is that here if R minimum by R is omega, then what I can do? I can replace R minimum with nothing but omega into capital R. So, that is what is done in the previous equation. So, here you can see for R by R greater than 1, TL minus T saturation PL has to be greater than 2 sigma T saturation at given pressure into VLB divided by this in place of R minimum, I will be getting R into omega, which is function of theta comma 2 gamma. So it means that from this particular equation, if I just put the equality sign, I can say that there exists some critical radius R star if the gas entrapment radius is less than that critical radius, then all these sites will not be active nucleation sites. But if the radius is greater than that, then only the nucleation sites will be actually active. Is this point clear? So if I see the number distribution function of cavities as function of minimum required radius, then I will be finding that if R critical, so typically we can assume that because I will be having cavities randomly distributed. So whenever we have any random distribution, it should satisfy our Gaussian curve. Okay. So once it is satisfying the Gaussian curve, then R star is the minimum required radius above which, or the critical radius above which only nucleation sites will be active. So on the Gaussian curve, if I have to find what is the number of active nucleation sites, that will be integration from R star to infinity d n dash c divided by dr min into dr min. Okay, where this is nothing but the number distribution function of the cavities. Now one experimental evidence is given over here, where a copper surface is properly developed in order to create some cavity sizes, and it has been found during the experiment that what are the number of active sites on per centimeter square of the surface. So here you can see when this is plotted as the function of critical radius for different fluids, it shows behavior something like this. And here you can clearly see that whenever the value of critical radius is being decreased, the number of nucleation sites are actually increasing. Whenever R star is having large value, then number of active nucleation sites are less. When R star is small, then the number of active nucleation sites are actually more and more. Okay, so now, till now what we have done, we have considered different situations which can show that how vapor can nucleate in the cavity and how it can come out of the cavity. Once the vapor is coming out of the cavity, what need to happen? Outside the cavity also, liquid has to be superheated enough so that this vapor should not immediately condense. Is this point clear? So initially we were talking about what is happening within the cavity, but once the vapor will be coming out of the cavity, it will be forming shape something like this. Now this shape can either grow or this shape can condense. It will be dependent upon the liquid temperature which is present in the surrounding. So whatever the required degree of superheat needed within the cavity, similarly there will be some required degree of superheat for outside also, and that required degree of superheat should also be maintained, then only my bubble will be growing. Otherwise, nucleation site will be becoming inactive. So it means that nucleation site can become inactive in two ways. One way is there is some vapor, but its radius is less than the R star value, then it is inactive within the cavity itself. And another way is that volume was able to evolve out of the cavity, but outside the temperature, the degree of superheat required for the liquid was not sufficient enough and it has immediately condensed. So this has deactivated the nucleation site when the vapor volume has come out of the cavity. So to understand this problem, what we need to do, we need to actually consider the transient conduction analysis. I can assume that I have a heater surface which is maintained at temperature Tw, and this Tw temperature has to be greater than T saturation, then only boiling phenomenon will be taking place. Now we know that typically inside a pool, whenever boiling takes place, we have vigorous mixing and convection currents which are taking place. But all these mixing and convection currents will be taking place in the region sufficiently away from the solid boundary. Very close to the solid boundary, where just nucleation is starting and the size of the bubble, say in the range of sub-millimeter, then I can find certain space where the pure conduction effects are actually taking place. So, the transfer of heat is because of actually pure diffusion, because this is the portion very close to the surface, maybe in the range of say 10 micron or 15 micron, where there is no effect of the convection because of the no slip and all other conditions. So, in this situation what will be happening, there will be formation of a thermal boundary layer. So, when the thermal boundary layer will be forming, we will be finding that TW temperature is there and say the bulk of the liquid is at temperature T infinity. So, outside the thermal boundary layer my temperature will be actually T infinity. Let me consider that Y equal to delta T is the thickness of the thermal boundary layer. So, this is my direction Y. At Y equal to 0, I am pointing at the surface, and whenever my Y is equal to delta T, then I am pointing at the maximum thickness of the thermal boundary layer, outside which my temperature is actually T infinity. Now, in this situation, you can consider that here I have some vapor bubble which just has nucleated, but now we need to decide its fate, what will be happening to it, whether it will be growing or whether it will be dying down. So, what I need to do in order to understand whether it will be dying down or whether it will be growing, I need to determine the temperature at the top portion of this particular bubble. So, for that I need to solve the transient heat conduction equation in the liquid portion. So, once I will be solving the transient heat conduction equation, I can assume that my theta is a parameter which is T minus T infinity. We know what will be transient heat conduction equation, del theta by del T equal to alpha L, which is thermal diffusivity of the liquid, because we have to calculate only the temperature of the liquid. So, it is thermal diffusivity of the liquid into del square theta by del Y square. Is this point clear? Because I am considering conduction only in the one dimension. What are the boundary conditions to this? Initially, whenever I will be just starting the heating process at time t equal to 0, everywhere temperature will be equal to T infinity within the liquid. So, that is why theta is equal to 0 at t equal to 0. But when y is equal to 0, I have heater surface which is maintained at temperature Tw. So, I can say that theta will be equal to theta w, which is Tw minus T infinity at y equal to 0. And another boundary condition is when y is delta T, temperature is becoming T infinity. So, theta is 0 at y is equal to delta T. So, this is a very simple equation. I can easily solve this using the basic heat transfer, and if I solve this transient one dimensional heat conduction equation, I will be getting my temperature profile as theta by theta w equal to delta T minus y delta T plus some term cosine and exponential. Now, if I plot this temperature profile as function of y by delta T. So, what I am plotting over here is T minus T infinity divided by Tw minus T infinity. So, Tw minus T infinity is the maximum temperature gradient. So, of course, at y equal to 0, temperature is Tw. So, this graph will be starting from 1, and at y equal to delta T, this will be becoming 0 because temperature is T infinity. So, how the solution will be marching with time? At t equal to 0, I will be having some sudden jump because everything was at T infinity. When the solution will be marching with time, this is how time will keep on increasing. And corresponding to the steady state situation, I will be having nothing but a straight temperature profile which will be corresponding to steady state solution. If we keep our value of time very large, after that the temperature will not change and it will establish nothing but a linear temperature profile within the liquid layer. Is this point clear? Now, from the steady state solution, I know that I have some linear temperature profile which is adjusted between this point and this point. So, because of this linear temperature profile, if I consider that my top portion of the bubble is y equal to b. What is the top portion of the bubble? Top portion of the bubble is representing nothing but y equal to b. So, now from this known temperature profile, I can calculate the value of y, I can calculate the value of temperature at y equal to b. Now, if this temperature of liquid at this point, if it is representing the required superheated state of the liquid, then bubble will be growing. If it does not represent the minimum required superheated state of the bubble, in that scenario, what will be happening? The bubble will be actually collapsing. So, first point, we need to make some assumption over here. Typically, whenever people have done analysis, what they assumed that the vapor which is coming out of the cavity, it is in the form of a truncated sphere. So, first assumption is it is a truncated sphere and this particular vertical height is nearly equal to 2 times of radius of the cavity, and in terms of the radius of the bubble, it is 1.6 times of radius of the bubble. Is this point clear? So, this is an assumption over here. This is a pure assumption. If now we know the equation for required degree of superheat, the equation was TL minus Tsat equal to some quantity. But this TL now we need to calculate at location E, which is nothing but y is equal to b. Is this point clear? Immediately adjacent to the vapor, because if temperature of the liquid at this point is satisfied, then of course at all other locations it will be, because it is closer to the wall, it will be satisfied. So, I am just checking the extreme situation. Now, in this extreme situation, what I can do, I can define theta sat. So, this T sat, I am just defining T sat minus T infinity as theta sat. Now, what I can do, in this equation, if I substitute y equal to b, what I will be getting? I will be getting the temperature of location LE. Is this point clear? If I substitute y equal to b, I will be getting temperature at this point. So, in this equation now, I will be substituting y equal to b. So, if I substitute y equal to b, what I find is theta LE by theta W equal to, and again I have taken this equation with minus from this. So, I am finding theta sat by theta W plus some terms. Is this point clear? So, what is this? Now, this is the equation which is representing the value of temperature at topmost point of the bubble. But whose temperature it is representing? It is representing temperature of liquid. So, you have to understand this point, that when I am considering the one dimensional analysis, I am assuming that temperature in this plane is uniform. So, these all are nothing but constant temperature lines. So, you should not get confused that equation I am solving purely for the liquid, but I am calculating temperature of liquid above the vapor. So, I am not solving equation in this portion. I am solving equation in any portion where I have pure liquid present. And of course, whatever the temperature is at this point, same will be applicable for this point as well. So, if I plot this equation, so here you can see theta LE by theta W, same quantity, and here I am having delta T by Y, again the same quantity Y by delta T. So, it means this equation can be represented on this plot. So, when I am plotting this equation, I am finding this dashed line. So, this is the solution of theta LE by theta W. So, now you can see this represents the minimum required degree of superheat which is required for liquid in order for the bubble to grow. This temperature is larger in this zone. So, it means in this zone if any vapor volume is forming, that will not be able to sustain and it will be condensing. Same here also you can see in this zone the steady state temperature is less in comparison to the minimum temperature required to sustain this value. So, that is why it means that only this is the zone where I will be able to sustain the boiling. So, it means that now if I can find out the solution by just combining steady state solution with this required condition of superheat at these 2 points, I can calculate what will be the appropriate radius band that has to be satisfied in order for the bubble to grow. Is this point clear? All are clear with this idea? So, what I need to do now, if I have to find out the solution of these 2 points, what I need to do? Of course, I need to simultaneously solve the steady state temperature profile and the minimum condition. That is what I will be doing now. So, what is steady state temperature profile? Steady state temperature profile is when T is approaching to infinity. So, in this equation, if I substitute T approaching to infinity, E1 by infinity will be becoming equal to 0 and steady state temperature profile will be nothing but delta T minus Y by delta T. So, my steady state temperature profile is simply this. And second is, this is the equation which tells me, the minimum required degree of superheat for liquid to allow the bubble to grow, and if I have to find these 2 points, then ultimately simultaneously I need to solve these equations. So, now if I combine this equation A with the steady state solution equation B, I will be getting one quadratic equation for radius, and if I find the roots of this quadratic equation for radius, I will be getting one minimum and maximum value of the critical radius. So, whenever this sign is plus, the value will be maximum, whenever sign is minus, value will be minimum. So, it means that I have some critical cavity mouth radius, within that band only I will be having the growth of the nucleation. If my cavity is smaller than that critical value, then also nucleation site will not be active, and if my cavity radius is greater than that value, if I have a very extremely large, excessively large cavity, then also nucleation will not be able to sustain. All are clear with this point? So, here you can see that this value of cavity radius, if I plot, then at some value of theta w, which is Tw minus Tsat, at some value of theta w, this entire part will be 0 and I will be having the unique value of the critical radius, and typically this is the point from where actually nucleation will be starting, and from where actually this required degree of superheat will be met up to the bubble. And if I go above the towards the higher values, then I will be getting some minimum and some maximum value of radius. So, if I am operating within this band, then all my nucleation sites will be active which are having mouth radius identical within this range, and if I am going out of this range, then I will not be able to meet this. And typically this curve, because here you can see lot of thermophysical parameters are involved. So, this curve is plotted for saturated water at atmospheric pressure conditions. You can see this band of radius is dependent upon thermophysical properties. What it means that if a particular surface is working fine for one particular type of liquid vapor combination, it may so happen that for other type of fluid this surface will not be working, because for that particular surface we have to design the cavities based on the values required for that surface. Maybe so if you want to continue, then we can continue for some more time. Otherwise what we can do, I can take one maybe one more session, just brief session of about 30-40 minutes to complete the rest of the portion. So now it will be your lunch time, and I think we have gone 1.5 hours. Okay, so probably let's stop. Today I think you have session from 2:30 to 4:30. Okay. Maybe then tomorrow at some time we will have one small quick session of about 40 minutes. Okay. So where I will be covering the remaining portions. Up to this point, if you have any doubt, that you can ask. Theta W is there, so it is TW minus T set. If number of cavities are very, yes, if number of cavities are very close, but all have to be active, all have to be active. So if all are not active, then it will not happen. Then you can say that Leidenfrost effect can take place even at lower temperatures. Any other question? Okay, so I think you can go for lunch. Probably we will have one more session then tomorrow. Yeah.